In this video, we're going to be looking at another type of reaction known as an acid-base neutralization reaction. So you've probably heard of acids and bases before and that they neutralize one another. So what that means, what an acid-base neutralization reaction is when an acid gives a hydrogen ion sometimes also referred to as a proton because that is very literally what it is, to a base. So this is a proton transfer or hydrogen ion transfer reaction, and they're often written to look like double replacements. So double replacement was one of the kind of patterns that we saw for how atoms often move, where we have ion swapping partners. So acid-base neutralizations are a little bit different because acids are actually not ionic compounds, but in this case, they're behaving like ionic compounds. Because they are transferring H+, they are giving up an ion, even though they themselves are not an ionic compound. They function in very much the same way as ionic compounds. So we want to be able to recognize when an acid-base neutralization reaction is happening, and to do that we need to recognize acids and bases and what those molecules actually look like. So an acid is a substance that produces hydrogen ions or protons, H+, in solution, and gives that H+ to a base in a neutralization reaction. Acids are things that tend to have low pHs in solution. At room temperature, by low we mean less than 7. So you've probably heard of pH as a way that we measure how acidic or basic a solution is. Low pHs are acidic solutions, high pHs are basic solutions. So these are all kind of some general properties of acids, but how do we look at a formula or look at a chemical and know that it is an acid? Well, that is going to vary a lot depending on like what types of acids you're dealing with, but some of the most common types of acids that you will deal with are going to involve hydrogen, clearly, since they are producing hydrogen ions in solution. They must have hydrogen in them to begin with, and they will often have chemical formulas that start with hydrogen. And for the purposes of this course, that is kind of going to be our red flag that something is an acid, is that if its formula starts with H, we are going to treat it like an acid under the vast majority of circumstances. So some examples of acids that you might see. HCl is hydrochloric acid, is one you've handled in the lab already. H2SO4 is sulfuric acid, is another common one. H3PO4 is phosphoric acid, and HCN is hydrocyanic acid. So in each of these, we see that hydrogen is the very first thing listed in our formula, and that means that those hydrogen ions are acidic. Another good example is acetic acid, is the acid component in vinegar. And you'll notice in this one that we actually have hydrogen listed twice in the formula. There is one hydrogen out in front, and there are 3 more listed later in the formula. And that's because not all of the hydrogens are acidic. Not every compound that contains hydrogen is capable of functioning as an acid. Specifically, the hydrogen generally has to be involved in a really highly polarized bond. The same types of bonds that lead to hydrogen bonding between molecules also tend to lead towards molecules being acidic. So in this formula of acetic acid, what this formula is telling us, or the way this formula is written, what it's telling us is that this hydrogen is acidic, but these ones aren't, and that's why they're separated like that. So in these other ones, we have two acidic hydrogens in this one. They're both listed out in front, means they're both acidic. In H3PO4, all three of them are put out in front, meaning all three of them are acidic. So whatever hydrogens are written at the front of the formula, that is very frequently a sign that those hydrogen atoms are acidic. And any listed later in the formula may not be. Acid formulas aren't always written like this in the world at large, but for the purposes of this course, they will be. For the acids that we're dealing with, that is common practice. So bases, on the other hand, are things that produce hydroxide in solution. And they take the hydrogen ion from an acid in a neutralization reaction. And they tend to have high pHs in solution. And at room temperature, that means greater than 7. At room temperature, 7 is considered neutral, which is right in between acidic and basic, and anything below 7 is considered acidic, anything greater than 7 is considered basic. At other temperatures, that does change, but for now, room temperature is good enough. So in terms of formulas and structure, bases are actually considerably more diverse. So we're going to focus on just one of the more common sort of categories of bases, and that is hydroxide compounds. So ionic compounds involving hydroxide, when they dissolve in solution, produce hydroxide in solution, which is pretty straightforward. So many common bases are ionic compounds containing hydroxide ions. So for example, things like sodium hydroxide, potassium hydroxide, barium hydroxide, and there are plenty of others, but those are some of the more common ones. There are lots of other types of bases that exist, and you might see some in a few examples here and there, but for the most part, we're going to focus on these hydroxide bases because they're the ones that you do encounter most often in introductory chemistry courses. So now that we know a little bit about what acids look like, their chemical formulas tend to start with H. What bases look like, their chemical formula is going to most often contain hydroxide. When we look at a neutralization reaction, we said it looks like a double replacement, except that our acids are not actually ionic compounds. We can see H and Cl, both nonmetals. We would consider this to be a covalent compound, generally speaking, but we know that this hydrogen is going to be lost as a hydrogen ion. So our acids are essentially behaving like ionic compounds, even though they technically aren't. They're going to function very much the same way. So for example, one of the simplest neutralization reactions, most common neutralization reactions, is between hydrochloric acid and sodium hydroxide. We can see we have a typical example of an acid here where a formula starts with hydrogen, and we have a very typical example of a base where our formula contains a hydroxide. And so we can treat this very much like a double replacement reaction where our ions are swapping partners, just keeping in mind that the hydrogen ion is kind of functioning as an ion where we normally wouldn't expect HCl to be acting like an ionic compound. Acids actually do. So we're swapping the hydrogen ion with the cation from our base, which means that we are going to end up with sodium paired with chloride and H paired with OH. HOH is more commonly written as H2O, as water. So part of why these are called neutralization reactions is that you start with an acid, which has a very low pH, and a base, which has a very high pH, and when you mix them together, you're creating things that are closer to neutral, or in this case, completely neutral in pH. Water by itself is neutral. It is capable, actually, of functioning as either an acid or a base, depending upon the context, but by itself, it is completely neutral. Sodium chloride, also completely neutral, neither an acid nor a base. So we've taken these two things at sort of opposite ends of the pH scale, and we have neutralized them. We have brought them to the center by reacting them together. We end up with a solution that is completely neutral, or at least much closer to it, depending upon exactly what acid and what base you mix together. So in this example, our reaction is already balanced. We don't need to add any coefficients or anything, but that's not always going to be the case. So let's look at one more example. Let's react phosphoric acid and let's do potassium hydroxide. So in this one, when our ions swap partners, we want to make sure that we are thinking about the charge on our ionic compound. So when our hydrogens and our potassium swap partners, I'm going to end up with the potassium paired with the phosphate, and I'm still going to get water as one of my products, but we need to make sure that everything is neutrally charged here. So water is good to go. K3PO4, we know that, or sorry, K with PO4, gave away the answer. K is +1 as an ion, and the phosphate ion has a -3 charge. So that means that we're going to need 3 potassium ions for every 1 phosphate ion in this formula in order for that to be a valid ionic compound. Now that means we're going to have to add coefficients to balance our reaction. So remember that we always first need to identify what our products are going to be before we go back and adding coefficients to balance. So we identified our formula for our product here based on the charges. We know that the charges have to add to 0, so I need 3 positives to balance these 3 negatives. And water is always going to be one of the products for your neutralization reaction if you have a hydroxide base, which we will for this course. So to balance this, I currently have 3 potassium ions on the right and only 1 on the left. So I can put a coefficient of 3 in here. That also gives me 3 hydroxide ions, which paired up with my 3 hydrogen ions to produce 3 water molecules. So since we had 3 acidic, there we go. Since we had 3 acidic hydrogens that needed to be neutralized, we need 3 moles of hydroxide in order to do that. Each hydroxide ion in our base is only able to grab onto 1 hydrogen ion, and we had 3 in our acid. So to completely neutralize 3 acidic hydrogens, we need 3 hydroxides, and that is reflected in the formula of our products as well.